Okay, this is our induction video number 2. And I just want to give you 2 more examples on series proof. The first one I'm going to prove is that, and this will be a decreasing series. So 10 plus 2 minus 6 minus 14 minus, and this now is going to be 18 minus 8n. I claim that that will always total to n times 14 minus 4n, okay, for all natural numbers. And so I want to prove that true. Here we just note that this has a common difference of negative 8, right? So the terms are going down by negative 8. You would add negative 8, add negative 8, add negative 8, and so forth. Okay? And the second one I'm going to do is one that has an odd difference. So we'll again start with 10, but this time we're going to go up by 3. So 10 plus 13 plus 16 plus 19. And the nth term generator here is 3n plus 7. And I claim that this will always equal 1/2 times n times 3n plus 17. And I'm also going to claim this is true for all natural numbers. And again, you just might want to note here, this has a common difference of 3, which is an odd number. This is a common difference of negative 8. It's even, but it is decreasing. So both of these give a little twist on what we've already seen. Okay, we'll do the black one first. Okay, for the black one, we need to show that a sub 1 is equal to f sub 1. So that's going to be 18 minus 8 times 1 is supposed to be the same as 1 times 14 minus 4 times 1. And I'll put a question mark there. Again, a quick review. Remember how this comes about is you go into this and replace the letter n with the number 1. Where this comes about, you just go into this and replace the letter n with the number 1. And we have those 2 statements. So let's verify that that makes sense. We have 18 minus 8, and this is 14 minus 4. And sure enough, 4 is equal to 4. Okay, so that's true. Now, for the second statement we have to show is a sub k plus 1 plus s sub k is equal to s sub k plus 1. Okay. And again, very similar to what we just did. For this k plus 1 statement, you're going to go into the nth term generator and replace the letter n with k plus 1. So I have 18 minus 8 times k plus 1. Okay, for the kth partial sum, I go into the nth partial sum up here in red, and I replace n with k. K times 14 minus 4k. And for the k plus first partial sum, I again go into this red term, but now I replace the letter n with the expression k plus 1. Be careful, it is k plus 1 in parentheses times 14 minus 4 times k plus 1 in parentheses. Okay, and then we just have to see that this is true. Okay, so remember, so this comes from here, replacing the letter n with k plus 1. This comes from here, and we're replacing the letter n with k. So that gives us the term here. And the last expression, again, comes from here, but now we're replacing n with the expression k plus 1. So everywhere there's an n, put a k plus 1. Okay, and now let's just go ahead and do the algebra and verify this works. Just be careful with distributing 18 minus 8k minus 8 plus 14k minus 4k squared. That's the left side. And on the right side, I have k plus 1. I'm going to clean up this second set of parentheses here. This is 14 minus 4k minus 4. or cleaning it up a little bit more, k plus 1 times 10 minus 4k. I will have to distribute that. On the right side, what I've got minus 4k squared, just doing these in decreasing powers. That takes care of that. For the k's, I have 14 less 8, which is 6 k's. And for my constant, I have a 10. So again, the question is this true? Well, let's see. The right side, I have 10k. I have minus 4k squared. I have a constant of 10 and minus 4k. And rearranging minus 4k squared, looking at my k terms, I've got plus 6k plus 10. And that's the same as what I have over here. Okay? Plus 6k plus 10. Okay, so they do check. No question at all. Okay, so I've done that. Pretty easy when you have an even common difference. Okay, now the second example is going to be what happens when the difference is odd. So that was our green one there. And we're going to have to do the same thing. We have to show that a sub 1 is the same as s sub 1. And we have to show that when we add a sub k plus 1 to the kth partial sum, we get the k plus first partial sum. Okay, so showing a sub 1 is equal to s sub 1. We're using the green. Well, let's go ahead and take this black one away so we don't have to look at it anymore. We'll take that away. Okay, so we're doing this green one that has the odd common difference. Okay, a sub 1 is s sub 1. 3 times 1 plus 7 is supposed to be question mark 1/2 times 1 times 3 times 1 plus 17. That's the question. So what do we have? 3 plus 7 over here. This is 1/2 times 3 plus 17. So this is 10, and this is 1/2 of 20. And sure enough, 10 equals 10. Okay, so that's true. We've got this one taken care of. Let me go ahead and erase that. Obviously, you can play this back to see that work if you're copying it down. And I assume you're taking notes when you watch a lecture. So here's the second thing we have to show. A sub k plus 1 plus s sub k is s sub k plus 1. Okay, so we have to show that's true. Okay, a sub k plus 1, we go into here and replace the letter in with k plus 1. K plus 1, still add the 7. Okay, and now for the kth partial sum, we go into here, replace the letter in with the variable k, 1/2 times k times 3k plus 17. And on the right side, this is the tricky one. We're going to go back into here, but now we're going to replace the letter in with k plus 1 in parentheses. So 1/2 times k plus 1 times 3 times k plus 1. Be careful, there's nested parentheses here, right? The n is being replaced with k plus 1. Okay, so we just have to show this is true. By the way, if the statement is true at the very beginning, this will be true. I do know that this does work out. I just have to verify it. So show sufficient work that I know that you know these two things are the same. Okay, 3k plus 3, right, plus 7, 1/2 k. And I suppose I can go ahead and just leave this because I've got a little trick I'm going to do here in just a second. In fact, let me back up here. You know, before I even distribute, I don't like these fractions, and you probably don't like these fractions either. Let's multiply both sides of this equation by 2. By multiplying by 2, we should clear the fractions, right? So every term we multiply by 2. Well, this is all one term. This is all multiplied together. So when you multiply by 2, that just wipes out the 1/2. And you simply get k plus 1 times 3. And I suppose I could do this, 3k plus 3 plus 17. Be careful, you're not there's no distributing going on here. This is simply 2 times this factor, and so those two wipe out. Okay, on this side, there is some distributing. We have to distribute the 2 into here. We have to distribute the 2 into that, and lastly, the 2 into there. So the left side, we simply write 6 times k plus 1, that takes care of 2 times this, plus 14, that takes care of 2 times 7. And in the last guy, when you multiply 2 times this, that takes away the 1/2. So k times 3k plus 17. If you don't want to do this, you could chase this down using common denominators. And on this side over here, this has a denominator of 1/2. You'd have to write this as 14 halves and write this as 6 halves times k plus 1. You could do that as well. Okay, let's go ahead and finish this, and then we'll be done with this example. So we have 6k plus 6 plus 14 plus 3k squared plus 17k. That's the left side. And we're seeing whether these match. So I have k plus 1 here, and I have 3k plus 20 there. So rearranging, I have 3k squared. How many k's? I've got 6 and 17, that's 23 k's, right? And my constant is 6 plus 14 is 20. And on the right side, I have 3k squares. I have 20 k's, and there's the 3 k's, which is what I was expecting, and there's the 20. So sure enough, it's probably not a bad idea to write a final statement. 3k squared plus 23k plus 20 does in fact equal 3k squared plus 23k plus 20. Done. Okay, so by induction, both of these statements are true. The one here that had the odd difference plus the one that had the decreasing even difference of -8. Okay, so this will get us going for tomorrow. For Wednesday, I'll go ahead and do another video where I do a complete proof that does not involve an arithmetic series. And then I'll give you another one that doesn't even involve series at all. Okay, happy inducting.